definition here, if we have a tree, then we will have a root. Every tree can only have one root. So when you draw the tree, remember, you will draw from the root first, go down. Go downward. Even though the tree we see outside is go upward, but here you need to draw downward. It is one-way direction, so that means a tree, it must be anti-symmetric. I hope you still remember what is anti-symmetric. So if you go down one way, that one is anti-symmetric, and then the rest you can go from here, go to the other, and this one we call it as a vertex. If I label this as A, I label this as B, all these are the vertex, plural vertices. Okay, so for the root here, we can label it as, it depends on the question. If sometimes we will put it as V0, which is the starting point, or we call it as the root of the tree. Now, the first definition here tells you that you can only have the path or the edges. This one we call it as a path. Go up from the root to the other vertices. You can only have one path, go to the other vertex, and the V0, which is the root, they cannot have any path go into the root. We cannot have this. Meaning that there should not have any in degree for the root. The root can only have out degree. You remember your in degree, out degree or not? In degree means going in, right? Out degree means going out. So they can only have the out degree from the root. What is the degree of in degree for the root here? The degree of in degree for the root, B0, 0, right? Then the out degree is depends on how many out degree we have. Okay? Now the second one is to sketch the diagram for the relation which are not trees and which are trees. So we can give some example here. Now if I put the root as the V0, then all these will be the vertex come from the V0. I can label this as A, B, C, D, E. This is C. So we can label all the vertices like this. All the path come from the root. Okay. So this is the example of a tree. Another example, you can see if I put this as the V0, then here I can put A, B, C, and D. Is this a tree? The direction will always come out from the root, so the direction will actually go down here. If you put the arrow, the diagram, it will be like this, go out here, go out here, go out here, but it is understood that it must be going down, so the direction must be like this. This one go here, but this depends on either D to C or C to D. It depends on the order pair given. Okay. Now, if the graph is like this, can I say this is a tree? Why not? Now, just now I say the root cannot have the in degree, right? But for these other vertices, they can have in degree. The rules is they can only have in degree of 1. So for example, if I come to this one, the in degree is 1. I come to this C here, the in degree also must be 1. When I come to the vertex D, the in degree must be 1 also. All the vertices, their in degree also must be 1. Then only it can fulfill the definition of a tree. So in this case, can you determine all the vertices whether the in degree are 1? All of them? No? Which one not 1? D not 1, right? The D in degree here is 2. Meaning that if you have one of the vertex, the in degree is not 1, then it cannot be a tree. Okay? So here is the example to show that it is not a tree. You can write the reason or justification why this is not a tree. You can say because there exists 2 paths from where to where? If I put here is E. So you have B, E, D, go to D, V0 to D, 1 path, V0 to D by V0, E, C, D. So you can go through 2 different ways. One is V0, E, go to D, and another one is V0, E, C, D. 2 different paths go to the same destination from V0 to D. If this happens, then it is not a tree. Okay? So now we have this condition to determine a tree or not. If I have this A, B, C, D, E, the graph like this, is this a tree? Tree or not? No, not a tree. Why it is not a tree? Because the root, if let's say the root is V0, it is not connected to the A, B, and C, right? Okay, so we just say that no path from V0 to C. Or you can say no path from V0 to A, or no path from V0 to B. As long as there is one vertex that is not connected, then it is not a tree. If it is a tree, all the vertices you have must be connected. Understand that? At the back, can you see my writing? Can I? Okay. Now, since I have introduced you the definition of a tree, then followed by this, we will have the theorem. Okay, repeat the one that we said just now. How to put it in the theorem. Have you done? Okay, this is the theorem here. They say that if you have a tree, the T here represents the tree, and the V0 is the root, then they will have no cycles in T. Another way to say is the cycle like this, just now that one. This one, so this one considered as cycle. And then the V0 is the only root in T, meaning that we can have one root only. Then the V0 has the in degree of 0, no in degree for the root. And the other vertex has in degree of, just now I said what is the in degree of other vertex? 1. Yes. So this tree will be the first theorem to define a tree. How do you know that it is a tree? They must not have a cycle. You can only have one root. Then the in degree of the root must be 0. Other in degree of other vertices must be 1. If not fulfill one of these, and then it is not a tree. Okay? Next one, this is the tree where we can have the level of all the vertices like this. Now we want to see what is the relationship when we label it like this. Actually, this is like the relation in a family also. The top one, you can say it is a parent. The below here, it can be the children of the parents here. And then below here, it can be the grandchildren. Then the same level here, it can be the sibling. So all these below the A here, you can say it is a descendant, like the relationship in your family. Okay? Now, can you give me the example? Which one is the parents of which one? Who is the parents of C? A. A is the parent of C. Now another word that we use for the children is offspring. Who is the offspring of B? Which vertex is the offspring of B? Yes? E. Okay? So as I say, the offspring is the children. So in this case, the children of B is E. So we will say E is the offspring of B. Okay. Who is the sibling of F? Sibling of F. G, okay, the same level one. And the descendant? Which one are the descendant of A? Huh? Which one? Descendant of A. And descendant of C. Which one? C. All the children and the grandchildren, right? So you have F, G, J, K. Are the descendants of C. So these are a few examples of the relation in the tree that we have drawn here. Of course, you can have others also. This is only example. Not necessarily only A can be the parents of C. Maybe you can say the D also be the parents of H and I. H and I will be the offspring of D. And then you can say the descendant of B is E. The descendant of A, you have A, B, C, E, F, G, H, I, J, K, and so on. Okay, so all these are the relation here for the tree. Huh? Now, next one, also the theorem of a rooted tree. Just now we have three definition for a tree. This one is another one. Also the condition to determine it is a tree or not. Now the first one is it must be irreflexive. What is irreflexive? Is irreflexive equal to not reflexive? No? No, right? If I say not reflexive, it doesn't mean it is irreflexive. Agree? Okay. Reflexive means you must have all the elements, like you have 1, 2, 3, 4, for example. If you have 1, 2, 3, 4, reflexive, you must have 1, 1, 2, 2, 3, 3, 4, 4. Then, if it is irreflexive, that means you cannot have you cannot have 1R1, you cannot have 2R2, you cannot have 3R3, you cannot have 4R4, right? All these are the irreflexive. So when they say T is irreflexive, means that you cannot have one of the relation here. Or must not be a loop back to itself. As long as you have one, then it is considered as not irreflexive already. Okay? The second one is T is asymmetric. What is asymmetric again? Remember? Recall back, what is asymmetric? Can have two ways or not? Can have reflexive relation or not? Cannot. So for the asymmetric here, it cannot take this also 1, 1, 2, 2, 3, 3, 4, 4, and also cannot be two ways relation. If you have 1, 4, then you cannot have 4, 1 for the 3. That's why just now I told you it must be one way only, right? Okay. And the third one is if AB belongs to the 3 and BC also, then AC cannot be belongs to T. Now this one will be the cycle like just now. You have AB here, BC here, and then AC here. So you cannot have this relation. AB, BC, and AC. Okay? So these three are the theorem 2 to define a rooted tree. Yeah? So I give you the example. If this is the B0, this is A, B, and C. So if let's say the C here, I have a loop back to C, then this one is not a tree. Why this is not a tree? Because it is, how do you say this is not a tree? Yeah, it is not irreflexive. because you have a look back, right? So whenever you have one of them, then it is not irreflexive. If I have these two ways, right? Then this is also not a tree. Okay, the reason is not asymmetric, right? Because this is a two-way relation. So for the tree, it must be asymmetric, one way only. So if you have two ways, that means it is not asymmetric. Then if this is a V0, A, B, C, and in this case, it is not a tree. What is the reason? If I give you the arrow like this, then you can say that there exists more than, from where to where? More than more than one path, or you just say exists two paths, Exists two paths from V0 to C. V0 AC, V0 ABC, two paths. So that are the two theorems for definition of tree. Next time you can just follow these two to determine whether the order pairs, they can give you in the order pairs, and then you decide by yourself whether it can fulfill all these properties or not. If the properties can be fulfilled, then you can just define it as a tree. If one of them is not, of course you will say that as the reason. Justify your answer that it is not a tree. Okay? Next one. This is the example I draw here already. Now, for the third example, this one is the binary tree, but this one without the label. They just want to tell you that the binary tree is the branches where the path here, you have two from each vertex. Two paths come out from each vertex. Like this one, you have two here, and then two here. Maximum is two. When you say that it is a binary tree, the maximum number of paths come out from the vertex is two. It can be less than two. Not necessarily every vertex also have two paths come out from them. Okay, you can have one, but maximum you can have is two. So we look at what is the level 3. Let's say you have now we draw this expression using the 3 to draw. When we draw it, we need to see which one is the root. From the bracket given like this, we need to decide which one will be the left hand side of the root and which one will be the right hand side of the root. If you look at this expression here, do you think which one will be the root? If the bracket here, left hand side is 3 minus 2 multiply y plus, you see the big bracket at the right, so you have y minus 2 minus 3 plus 1. Which one will be the first, the root here? First one. Then we will go to the left and right. So the middle is plus, right? Okay. Plus is the root now, meaning that at the left hand side of all these brackets, it will be the left hand side of the plus. All these will be the right hand side of plus. And when you label this left hand side, right, you need to choose again which one is the root of the left hand side here. Minus. Correct? And the right hand side, the root is minus also. Then you go down to the left again. So at the left of minus, here we have 3. At the right of minus, we have multiply as the root. Then left hand side of multiply, we have 2. At the right of multiply, we have y. When we come to the right hand side, just now the root is minus, so when you go to the left of minus, you have y minus 2. So you need to label the minus as the root first. Then go down. At the left of minus is y. At the right of minus is 2. Then you go to the right, the root will be plus 3 and 1. This is the level 3. Okay, later I will tell you all these sequence, which one we need to put first, which one we need to put after. If we do the different order of search, then we will use a different sequence. So for this normal one, we just see the bracket first, which one should draw at the left of the root and which one is at the right. So here is the big bracket. That means the whole thing here should be at the left of plus. Here another big bracket. So these two must be at the right of plus. Follow the which side is it. You cannot simply change the side. Like this one 2 multiply y. The 2 must be at the left of multiply. You cannot put the 2 at the right of multiply. Even though the answer you get will be the same, right? Because 2 multiply y and y multiply 2 are the same. But when we draw the 3, we must follow the sequence. So this is only the example for the level 3. Later we will go to more detail about this. Now, positional 3, meaning that we will label the vertices, follow their position. If let's say I have a binary 3, so when I label the 3, I will label it follow the position. let's say here is the at the left hand side the path, so I will label it as the L to represent the left hand side, and this one I will write as R, which is the right hand side. Follow their position. So this is another side R here. This is another one R here. This is left. This is left. Not necessarily must have two paths. As long as the maximum is 2, then the rest you can have one path only. Okay? So this one we label follow their position. If you have binary, that means we only have 2 maximum. If let's say I have n, because this is considered as n3, I can have 3, 4, 5, 6 and so on. So if this one is 3, then maximum how many? How many maximum path? If this n is 3 now, 3. So here I can have maximum. How many paths come out? Binary is 2, right? Binary means 2, so binary maximum you have 2 paths, left and right. If now if the position 3 now, I change to position 3 here, the n becomes 3, 3. So how many paths maximum here? 3, right? So we will never follow their position. The left hand side, if I label it as 1, so every time I will label the left hand side as 1. 1, 2, 3. This one come down, so you have 2 here. This one go to the left, you have 1 here. Go to the left, another 1 here. So this is an example of the positional 3, 3. Follow their position. Left is always 1. Middle is always 2. 3 will be always at the right hand side. Okay. Now 1 o'clock, you need a break. I start a little while only, right? Okay, you take a break, then later we continue.